Decision trees are amazing tools for finding patterns, but they have one huge blind spot. They just don't get the concept of time. So in this explainer, we're going to show you a really cool trick for how to teach a decision tree to see the past, so it can start predicting the future. All right, here's how we're going to break it down. We'll start by getting our heads around the forecasting challenge itself. Then, we'll look at why decision trees and time-based data don't naturally play well together. The real magic happens in Section 3, where we literally give the model clues from the past. After that, we'll put our creation to the test, and then we'll wrap up by seeing how this gives us a powerful new tool in our data science toolkit.
So let's jump right in. How do we even begin to tackle a forecasting challenge? Well, let's start with a classic example to see what we're up against.
The data we're going to be playing with is the monthly airline passengers dataset. It's a famous one, and for good reason. It's super simple. It just shows the number of airline passengers month by month for about a decade. It's kind of the perfect, clean example of what we call a time series, just a single stream of numbers marching forward in time. Okay, so we've got our data and we've got the tool we want to use, a decision tree. But here's the thing, there's a fundamental mismatch. They just don't speak the same language. And this slide right here, this gets to the heart of the problem. On one hand, you have our time series data, which is basically just one long line of numbers. But a decision tree, it lives in a world of tables. It needs organized columns, what we call features, to use as clues for making a prediction. It's like trying to fit a piece of spaghetti into a spreadsheet cell. It just doesn't work. So, that leads us to the million-dollar question, right? How do we bridge this gap? How can we possibly translate that simple single timeline into a rich, structured table of clues that a decision tree can actually sink its teeth into?
Well, the answer is a little bit of data science magic called feature engineering. We're not getting new data. We're going to cleverly create the clues our model needs from the data we already have. We're essentially turning our simple timeline into a treasure map for the decision tree to follow.
And we're going to pull off this little magic trick in two main steps. First, we're going to create something called lag features, which is basically like giving our model a memory. Then we'll create rolling statistics to give it a sense of the recent momentum, the trends in the data. So, first up, what on earth is a lag feature? Well, it's actually super simple. It's just a value from a previous point in time. It's like we're giving the model a rearview mirror, so it can see what just happened last month, the month before that, and so on. Check out this table. It shows you exactly how this works. For any given month, say March of 49, we create a new column called lag_1, and we just pop in the passenger number from February. Then another column lag_2 gets the number from January. We actually do this for the past 12 months, giving our model a full year of historical context for every single data point. All right, next up we have rolling statistics. Now, instead of just looking at individual moments in the past, we're going to summarize a recent chunk of time. This is all about giving the model a feel for the recent vibe of the data. Are things trending up? Are they going down? Has it been super choppy lately? For example, we could look at the average number of passengers from the last 3 months. But, and this is super important, we can't include the current month's data in that average. Why? Because that would be like giving the model the answers to the test before it takes it. It's called look-ahead leakage, and it's a big no-no. We're forcing the model to make a real prediction. No cheating allowed. Okay, the prep work is done. We've taken our simple, one-dimensional timeline and transformed it into this rich, multi-dimensional data set full of clues. So now, for the moment of truth, let's put our decision tree to the test and see if it can actually predict anything.
And voila! Look at this! This is what we've created. What started as just a single column of passenger numbers is now this beautiful, wide table packed with all sorts of historical context. Now our decision tree has something to work with.
So to see if this actually works, we gotta be fair about it. We split our data by time. We let the model learn from the first 80% of the data, and then we test it by asking it to predict the final 20%, a future it has never ever seen before. This is exactly how you'd use it in the real world. And now for the fun part. We feed all that training data into a decision tree regressor. It's like we've hired a little detective, and it starts sifting through all the clues we gave it, the lags, the rolling averages, looking for any patterns, any rules that connect those clues to the actual number of passengers. Okay, so here's the moment of truth. After all that work transforming the data, did it actually work? How good was the model at predicting those future months it had never seen before? And the result? We got a mean absolute error, or MAE, of 45.32.
Okay, so what does that number even mean? Well, simply put, it means that on average, our model's guess was off by about 45 passengers each month. Now, that's not too shabby for a first go, but there's always room to get better, right? This kind of technique, for instance, is brilliant for data with clear seasonal patterns like we have here, but it can have a tougher time with more complicated forecasts where you've got a ton of different things all interacting with each other.
Okay, let's step back for a second and think about the big picture. What have we really done here? What's the main idea we can take away from this?
So, what are the key takeaways? Well, first, we've seen that you can take time series data and reshape it for pretty much any model that likes tables. Those lag features, they give the model a memory. The rolling stats, they give it a sense of what's happening right now. And what we've really done is turn a tricky forecasting problem into a much more straightforward regression problem. And that really shows you that creativity and how you set up your data, that's a true data science superpower.
So, when you boil it all down, what did we do? We took a model that is completely blind to the concept of time, and through some clever data wrangling, we taught it how to use the patterns of the past to make a really solid guess about the future. Pretty cool, right?
And that really leaves you with a final, kind of mind-bending question. If we can use feature engineering to teach a model something as fundamental as time, what else can we teach it to see? What other hidden patterns are just waiting to be uncovered?